Welcome back to AE 3530, System Dynamics and Vibrations. In this video, we're going to go through example 6 from our notes. This example considers a rigid bar suspended by an inextensible wire with a force P of t acting only in the horizontal direction located at position B. Gravity is also included, and we're asked to determine the equations of motion using Lagrange's equation. The generalized coordinates that we're going to use for the system are theta 1 and theta 2. And we started off in class by going and defining a Cartesian coordinate system at the fixed point of the wire. That's where the wire connects to the ground. This will give us rotation that is positive in the counterclockwise direction. And then we went and drew several different position vectors, including RA, RC, RB, RC/A, and RB/C. I want to make just a quick correction here. We're actually going to need, instead of an RB/A, we're going to need a B/C. We're going to need RB/A instead. That's what we're going to end up using to define the position RB. We're now going to go through and write out what each of these position vectors are. We'll start off with RA. RA is going to be equal to L1, and that's the length of the wire, L1 times the sine of theta 1 in the I direction minus L1 cosine theta, and that's in the J direction. That's our RA vector. We'll then go and look at what RC is. That's to the center of mass. RC is going to be equal to RA plus the relative position vector RC/A. We now need to find what RC/A is. RC/A is going to be equal to, in this case, the total length of the bar is given as L2. So this will be L2 over 2 times the sine of theta 2 in the I direction minus L2 divided by 2 times the cosine of theta 2 in the J direction. And now, given that we now know RA and RC/A, we can now find RC. And RC is going to be equal to, we'll group up the terms, we'll get L1 sine theta 1 plus L2 over 2 sine theta 2. All of that in the I direction minus everything in the J, which will be L1 cosine theta 1, and up here in the RA vector, I also need to put a 1 in that theta because that's theta 1, plus L2 over 2 cosine theta 2, all that in the J direction. So that's the position of our center of mass. I'm going to go ahead, I'm just going to move this down because I'm going to end up drawing the position of this bar in what we're going to choose for our reference system. And I'm just going to need a little bit more space to the left there. So we want to define well, let's continue with our position vectors. So the next one that we need is RB. And RB is going to be equal to RA plus RB/A. And we're going to find that RB/A, this will be equal to, in this case, L2 sine theta 2I minus L2 cosine theta 2J, such that RB will be equal to the quantity L1 sine theta 1 plus L2 sine theta 2, all of that in the I direction, minus the quantity L1 cosine theta 1 plus L2 cosine theta 2, all of that in the J direction. Okay, so now before we move on, we're going to define our reference position that we're going to use for defining the potential energy. We're going to say that the reference potential energy, or the reference position, is when theta 1 and theta 2 are 0. I'm going to draw this right here. That's the wire. Here's our bar. That's our bar right there. Our center of mass right here. And then the position vector, draw right here. We'll call this rref. In this case, rref, we have two options on how to find this. We can just look at what it is and determine it based on what we see in our reference position. We could also take RC and plug in theta 1 and theta 2 equals 0. And in either case, we're going to find here that this reference position vector, this is going to be equal to minus. So in the I direction, it's going to be 0. But in the j direction, we're going to have minus the quantity L1 plus L2 over 2 in the j direction. And we're going to say here that the reference vector is needed to compute the gravitational potential energy. It's needed to compute the gravitational potential energy. And just to kind of harp on this point, you must choose a reference point where you can identify the position exactly. So your reference point can be any position you want, but you need to be able to define it exactly. So you could decide that your reference point is when theta 1 and theta 2 are both equal to 90 degrees or pi over 2. And then you would be able to define its position purely in the I direction, for example, but you must be able to define that. So choose a reference point where you can identify the position, exactly. So you cannot choose a reference position where theta 1 and theta 2 are unknown. You must prescribe values to them. Okay, now with all the position vectors defined, we can now move on and compute velocity vectors. We only need to compute the velocity vector for the center of mass, in this case, or RC, because that's the only object that has mass that is moving. The wire is moving, but it is assumed to be massless here. So we got RC up top here, and we can go and compute its derivatives. Remember that theta 1 and theta 2 are both functions of time, and since they're stored inside of another function, we'll have to apply a chain rule. So we're going to get here L1 theta dot cosine theta 1, that should be theta 1 dot, plus L over 2 theta dot 2 cosine theta 2, all of that in the I direction, plus, and in this case, because we have cosines and taking derivative of cosine gives you a negative sign, that will cancel out the negative in the front. So we'll get L1 theta 1 dot sine theta 1 plus L over 2 sine theta 2, all of that in the j direction. And that is the velocity vector, and I left out the dot on this RC, it should be RC dot. That is our velocity vector. We're now ready to move on and start computing the energies and the work done by the non-conservative forces. In this case, there's only one non-conservative force, that's that applied external force P of T, the one right here that I've just circled. That is our only external or non-conservative force. We'll start off with the kinetic energy. Start by computing that. We'll write here KE just so we know which energy we're defining here. And we use big T for the kinetic energy. So this is equal to 1/2 m times RC dot dotted with itself, which is equal to 1/2 m times the quantity L1 theta dot 1, theta 1 dot cosine theta 1 plus L2 over 2 sine theta 2. That quantity, that should actually be a cosine, and I missed out a term, so it should be L2 over 2 theta 2 dot cosine theta 2 quantity squared plus the quantity L1 theta 1 dot sine theta 1 plus L2 over 2 theta 2 dot sine theta 2, that quantity squared. And you can go and expand this and do some algebra, and you'll find that, and apply some trig rules as well, and we'll find that the kinetic energy is 1/2 m times the quantity L1 squared theta 1 dot squared plus L1 L2 theta 1 dot theta 2 dot times cosine theta 1 minus theta 2 plus L2 over 4, L2 squared over 4 theta dot 2 squared. Okay, for the potential energy, we now need to go and compute that. We're going to use the integral form in this case, although for a gravitational potential energy, you may be able to just figure it out on your own, but for this example, we're going to go and do the integral. We're going to have V is equal to the integral from the reference position, RF, to RC of minus mgj dotted with, we'll use a du here. It's a vector. This is going to be equal to minus mgj dotted with u evaluated at ref and rc. And this will then be equal to mg times the quantity L1 times 1 minus cosine theta 1 plus L2 over 2 times 1 minus cosine theta 2, and that is our potential energy. So we can write here that V is equal to mg times quantity L1 times 1, the quantity 1 minus cosine theta 1 plus L2 over 2 times 1 minus the cosine of theta 2. All right, we're now ready to look at the work done by the non-conservative force P of t. So we'll write here delta WNC is going to be equal to P of t, and it acts only in the horizontal direction. So that's going to be in the I direction, dotted with delta RB. So we now need to go and compute what delta RB is. And remember, these deltas represent virtual displacements, and they're not infinitesimal like a d would be, but they still obey the rules of differential calculus. So we're going to go and take a derivative. If we go back up and look at what RB is up here, we're going to go and take derivatives of this term or of this system, and then instead of pulling out a derivative of like theta 1 from the sine, when we take its derivative, we're going to pull out a delta theta 1 and then also a delta theta 2. And so what we'll end up finding is that this will be equal to the quantity L1 cosine theta 1 times delta theta 1 plus L2 cosine theta 2 times delta theta 2, all that in the I direction, plus L1 sine theta 1 delta theta 1 plus L2 sine theta 2 delta theta 2, let me rewrite that, delta theta 2 and that's in the j direction. We go and compute the dot product of delta RB with P of t. We will end up rejecting and losing out the j term, and we'll get here that the virtual work done by P of t is going to be equal to P of t times L1 cosine theta 1 times delta theta 1 plus P of t L2 cosine theta 2 times delta theta 2. And now we have our two generalized forces. This will be our Q, let's say Q theta 1, and this is our generalized force Q theta 2. So here's where you can see how these generalized forces, how we can define them in our chosen generalized coordinate system. And we can see that in this case P of t is modified by an L cosine term for either theta 1 or theta 2. Okay, with that, we are now done with step 4, and we're going to move on to computing our Lagrangian. Lagrangian is going to be L is equal to T minus V, which will be equal to simply 1/2 M times the quantity L1 theta 1 dot squared plus L1 L2 theta 1 dot theta 2 dot cosine theta 1 minus theta 2 plus L2 squared over 4 theta 2 dot squared, all of that minus mg L1 1 minus cosine theta, and that should be cosine theta 1, plus L2 over 2 times 1 minus cosine theta 2, and that is the Lagrangian. At this point, we're now ready to go and apply the Lagrange equation, or apply Lagrange's equation, we should say. Let me correct that. All right, so we're going to go and apply Lagrange's equation. To that end, we're going to write here that for theta 1, we're going to have d over dt of partial L over partial theta 1 dot minus partial L over partial theta 1 is going to be equal to Q sub theta 1. And then for theta 2, we're going to have d over dt times partial L over partial theta 2 dot minus partial L over partial theta 2, and this will be equal to Q sub theta 2. Okay, we're going to work with the theta 1 first. We're going to construct each of their components, and then we'll combine them to form the equation of motion. In fact, we'll just do components for each of these, and then we'll assemble them. We'll assemble them, and then we'll do theta 2. So we're going to start off with the d over dt of partial L over partial theta 1 dot. This is going to be equal to d over dt times the quantity m L1 squared theta 1 dot plus m over 2 L1 L2 theta 2 dot times the cosine of theta 1 minus theta 2. And we can now take the derivative with respect to time. We're going to need to do, well, the first term is going to just give us a theta 1 double dot, so we're going to get m L1 squared theta 1 double dot. The second term we're going to have to do a product rule. So we're first going to have m over 2 L1 L2 theta 2 double dot times cosine theta 1 minus theta 2. And then we have to do that product rule, so we're going to get minus m over 2 L1 L2 theta 2 dot times the quantity theta 1 dot minus theta 2 dot times the sine of theta 1 minus theta 2. And that is the first term in this Lagrange, or in Lagrange's equation for theta 1. For the second term, we're going to have that the partial of L over partial theta 1, this is going to be equal to minus 1/2 m L1 L2 theta 1 dot times theta 2 dot times the sine of theta 1 minus theta 2 minus mg L1 sine theta 1. Okay, so we can go ahead and start combining these. We're going to first get m L1 squared theta 1 double dot plus m over 2 L1 L2 theta 2 double dot cosine theta 1 minus theta 2 minus m over 2 L1 L2 theta 2 dot times theta 1 dot sine theta 1 minus theta 2 plus m over 2 L1 L2 theta 2 dot squared sine theta 1 minus theta 2. And then we're going to subtract the dl d over d theta 1, and that will make both those signs, let me get the laser, both this sign and this sign will make both of these positive right here, right here. So we're going to get plus m over 2 L1 L2 theta 1 dot theta 2 dot sine theta 1 minus theta 2 plus mg L1 sine theta 1, and then this will be equal to, if we go back up to our generalized force, it's going to be P of t L1 cosine theta 1. And then we can also eliminate the term with the mixed velocities, such that we'll get m L1 squared theta 1 double dot plus m over 2 L1 L2 times the quantity theta 2 double dot times cosine theta 1 minus theta 2 plus theta 2 dot squared sine theta 1 minus theta 2 plus mg L1 sine theta 1 equal to P of t L1 cosine theta 1. Let's go ahead and now do the second equation. We're going to get d over dt partial L over partial theta 2 dot, so we equal to d over dt times the quantity m L2 squared over 4 theta dot squared plus m over 2 L1 L2 times theta 1 dot cosine theta 1 minus theta 2. This will be equal to m, let's say m over 4 well, actually this should be an m over 2, shouldn't it? Let's just go back up here, because we have our kinetic energy, or in our Lagrangian, we have theta dot 2 squared. Oh, but it's going to cancel. When we bring this 2 down, it's going to cancel the 1/2 in front, so never mind. So we're going to have m over 4 L2 squared theta 2 double dot plus m over 2 L1 L2 theta 1 double dot cosine theta 1 minus theta 2, and then minus m over 2 L1 L2 theta 1 dot times the quantity theta 1 dot minus theta 2 dot times the sine of theta 1 minus theta 2. And that is it for that part. We'll now go compute the second part. Partial L over partial theta 2. This is going to be equal to 1/2 m L1 L2 theta 1 dot theta 2 dot sine theta 1 minus theta 2 minus mg over 2 L2 sine theta 2. And you can go and combine those two together. Just as a reminder, the Lagrange equation is d over dt partial L over partial theta 2 dot minus partial L over partial theta 2 equal to q sub theta 2. You can go and combine those, and we'll end up eliminating a mixed velocity term just like in the previous equation. And then we'll end up with the equations in the box shown here. You can see how this force that acts only in the horizontal direction is now applied in each of these equations of motions, and how the rotation affects the influence of that force. Okay, with this, we are done with chapter 1. And in the next class that we have, we'll start chapter 2 on single degree of freedom vibrations.